Okay, scientist named Oersted. He found that if you put a current through a wire, it would produce a magnetic field. So if you take a copper wire and you attach current through it, so a battery or a power source of some kind, one on either end, you can create a magnetic field around the wire. To determine the direction of the magnetic field around the conducting wire, compasses were placed in different locations around the conducting wire, and the north end of the compass needle was observed to determine the magnetic field. Okay? What way is that north end of the compass pointing to? Which pole? South. The south pole, okay, of the magnet. I'm not sure why I have that workplace readiness 10-4 square in my screen. It's driving me crazy. And I can't get rid of it. Okay. So we use two symbols. We use a dot and we use an X to represent the direction in and out of a page for the magnetic current, or for the current. So think of it as an arrow, right? You have a point and you have feathers. So the point is coming at you. You're seeing the tip of the arrow, so it is coming out of the page. And if you see the X, that's the tail feathers going away from you. It's going into the page. They had to come up with some kind of symbol system because paper is two-dimensional. When we write on it, it's two-dimensional. But yet, we're talking about a three-dimensional concept. Okay? So if I have something that has an X, okay? This is the circle is the cross section of a wire. Okay? And the X, whoops, wrong pen. And the X is the current running into the page. So we can see then if we were to take a compass and we put it here, it would point this way and then this way. As we move the compass around this wire, we would see this motion of the compass needle. Okay, that's what Oersted did. He just put electricity on either end of this wire, and then if this was the wire like this, he would see as he moved the compass to different points that the north would change as he went around the wire. That's what he saw. So what we can say then, here's our wire, cross section of our wire, and the current is going into the page, that this is the induced magnetic field. We use these rules to help us figure out different things. And we use our left hand because our left hand is going to be the negative particles moving, and our right hand is going to be for positive. Okay? Left hand for negative, right hand for positive. The left hand, if you look at any textbook designed in the United States, they talk about the right hand rule. which we call, or is called universally, the conventional current. We use the left-hand rule because what moves? Electrons. Are electrons positive or negative? Negative. So we look at the left-hand rule. Okay? That's the thing to remember. That if it's a negative, it's the left-hand rule. If it's a positive, you use your right hand. And the code word for that is conventional current. I don't know why the Americans use the right-hand rule. Any person you watch on TikTok, on Instagram, on YouTube, they all use the right-hand rule. They are talking about positive charges, and their students have to remember to switch to their left hand if they're talking about a negatively charged particle. Everywhere else teaches the left-hand rule, and I don't know why the difference. Just to be different? I don't know. The first rule that we have is the direction of the induced magnetic field. So it's the direction of the induced magnetic field around a conducting wire, because we're going to build on this and change it a little bit from rule to rule to rule. So if I have a current that's running into the page, my thumb is going to represent the current. I'm going to stick my thumb into the page, and my fingers show the direction of the magnetic field. Okay, so the direction of the magnetic field is going to go this way. You can't see it, this is very bad. Okay, it's going into the page, and it's going to go this way around the wire, the same way that the compass went. If it was coming out of the page, I would stick my thumb out of the page, and my fingers would run in the direction of the current. So if the current in the wire is coming out of the page, the induced magnetic field would have been this way, right around the circle, clockwise. Okay? First left-hand rule. Your thumb is the current, and your fingers are the induced magnetic field. Okay? All right. So in this wire here, and you need to know something. You have to be given either the magnetic field or the electron flow or the flow of current. You have to be given something of that information. So your thumb points in the direction of the left of the electron flow, and your fingers are the direction of the induced magnetic current. So here, the arrow shows that it's going this way. So I'm going to put my thumb this way, and my fingers are going to show. And so I show it by wrapping around like that. Okay? In this one here, if I saw these circles going this way around the thing, so I would start with the induced field, magnetic field. I could then tell you that the current or the electron flow is going this way. So in these notes, you see B representing magnetic field, and I we've already seen as current. Okay, we saw it in the electric fields and forces. So B now stands for magnetic field. We are introducing letters left and right. I know, you're so excited. If the current here is going up, then the magnetic field must be going clockwise. Okay? Left-hand rule. There's a star here. The left-hand rule only works for the flow of electrons or the flow of negative charges. You have to use your right hand if you want to use conventional current or a positive charge. So right hand, positive charge, otherwise known as conventional current. Okay? That's the introduction to the first rule. These are not complicated, there's just 3 of them. So if I was to take, I'm going to do this, see why I was standing up. If I was to take a wire like this, say this is my wire, and I attach a power source to it, which is a current running through it, the current induces the, we'll learn more in the next lesson, but if we're moving positive or negatively charged particles, we have motion, and in that motion, we can create this alignment of the magnetic field. And so it will create, electricity will go through the wire, it will create a north pole end and a south pole end, and then we know that it flows out of the north and into the south, and it creates this magnetic field. And so then you take a compass and you see the compass moving, then that's showing you that there's a magnetic field there.
And like the red usually is that the magnetic field or the compass?
This here, this was Orsted moving a compass, and so it was just, it happened to be moving in this direction. When he had the current like this, if this was his wire, the current was going this way into the page. He was able to show with a compass, if he put a compass here, that the North Pole would look like it's moving as it goes around this wire.
Sorry for the interruption with Tyson Glover. Please come to the office. Tyson Glover. Thank you.
Pardon me? Yeah, it's just the direction of the compass point moving. Yeah. Okay?
So like that's not where like the red.
No. No, it's just moving in this direction. Okay? All right. So conducting wires with currents running through can interact with each other due to their induced magnetic fields and whether they repel or attract each other. Just like we looked at yesterday with the magnets. If I take a north end of a magnet, will it attract or repel the south end of another magnet? If I take a north end of a magnet and I put it up to a south end of another magnet, will it attract or repel? Attract. If I take a north end of a magnet and I put it up against another north end of a magnet, it will. Same with south and south. We can do the same thing with current. If I have one current that's going into the page and one current that's coming out of the page. Okay? So I'm going to take my left hand. I'm going to show that my current is going into the page with my thumb. My fingers indicate that the induced magnetic field is going in which direction? To the left. It's going counterclockwise. Okay? So my induced magnetic field is going to go counterclockwise. If I take my out of the page and I go like this, which way is my induced magnetic field going to go? Clockwise. Okay, this is magnetic field. What do we see happening here? They are both going in the same direction. Are they going to attract or repel? They're going to repel. Okay? If I had two of them coming out of the page, this one is coming out of the page, and so my induced magnetic field is going to go which way? To the right. When I look at this one here, it's going to go which way? It's also going to go to the right. So right here, it's going down, and right here, it's going up. So what are we going to see between these two conducting wires? Attraction. Okay? Because we're still working on the same principle as magnets, north and south. All right. When a conductor, bring it a little bit closer so you can see better. When a conductor wire is wrapped into many loops, we end up creating a solenoid. So we've just taken the long piece of copper wire, let's say, and we've just wrapped it into loops like this. So it's still the same wire, but now it's got these loops around it. What happens is we create an electromagnet. Okay, so an electromagnet is a single wire that's put into multiple loops and attached to some power source. So here, when we look at this one, our power source says that it has a positive on the left and a negative on the right. And we can see that the wire is going to come from behind and go over top. And from behind, and so it's like wrapping around. If this was my wire, it's like wrapping around this way. From the back to the front, from the back to the front. Okay? And then it ends up at the... So one of the things we need to look at is which way are the electrons flowing? They're going to flow out of the negative end, and they're going to flow this way. Okay? Which means that they're going to come from behind. Electron flow is this way, this way, this way, and then it's coming out this way, and electrons will flow into the positive, right? For the attraction piece. Yeah, they're going out this way, so they're coming from, if we follow the path of the wire. Stop. If we follow the path of the wire goes from behind out front. So we're just following that wire pathway. Okay? When the current's running through the conductor, the solenoid will produce an induced magnetic field around the solenoid. So what they did was they curled it, and you can see here that the current is coming in from this way, going in behind and coming over front. And then over front, and then over front. and then it comes down this way. So our electrons are going in on the left and out on the right. Okay? So if I was to take my fingers and show that the coils are going this way, so now the purpose of my fingers are changing. Before they were induced magnetic field, I can see that my thumb is going to point this way. Okay, my fingers curl from back to front, and my thumb points to the left. Okay, so again, compasses were used to prove this concept. They always did something first and then they figured out what was going on afterwards. All right.
So that's still
No, our fingers, we're doing something different now. Okay, so we're going to end like this piece here. That was the first hand rule, this part up here. Now we're moving into a new concept, and it is the second left-hand rule. So the second left-hand rule does the direction of the induced magnetic field around a solenoid based on the direction of the current moving through the conducting wire. Okay? So you can see here that the fingers are pointing in these ones are hard to read. The fingers are moving this way around the solenoid because the electrons are coming over top and then going in behind. They're coming over top and then going in behind in this particular picture here. And we can see that here's the positive end and here's the negative end. So it's going to go over top and then come out from behind. So that's going to be the direction of our electron flow. Which? Yeah, that's as high tech as we get. Okay, from the front to the back. Okay, here if we look at this one works the best. Here's the negative and here's the positive end. The electrons are going to flow this way. Okay, and so we see that the wire curls from the front to the back, from the front to the back, from the front to the back. So it comes, I need to get that right, from the front, yeah, and then it comes out this way. Because it comes over top and goes behind. Over top and behind. And so over top. So it's showing you that the current is coming from over the top and then going around. So it's essentially, if it's coming this way, right? It's going over top. We can't show it going this way. It's coming this way. Okay? And so then that means that our thumb now indicates the direction of the pole. Our thumb is now north. And our fingers are direction of current. Okay? I know, it's confusing and it's lots. Curl your fingers of your left hand in the direction the electron flows in the coiled wire. So you have to pay attention to your battery source. Remember, if we see this system here, and a wire, what side is this? positive, and this side is negative. You have to be able to read a battery this way or the power source this way. You have to look for a positive or a negative, or you have to look for an electron flow arrow. There's 3 different ways you can be shown how the current is moving through the wire. Okay? So I'm helping you to future decode questions. All right. When we look at this one here, it's starting here. This X represents where we're starting from, and it's going to come over top and go behind. So it's going to go from the back to the front, which means that our north is pointing this way. This one here, here's our X. This is our X marks the spots where we're starting from. It's going to go over top and then go behind. So it's going this way. Our electron flow is this way, which means that our thumb is going to point in north to the right. When I look at this piece here, we see that it's going this way. The people are all sick. Yeah. Okay, so you're going to curl your fingers of your left hand in the direction of the electron flow or the current flow in the wire. Keep your thumb straight. So this is going into the page. The electron current is going into the page, and it's coming out of the page here.
But for this, since it's what is it?
The current, the solenoid?
Yeah, we do it in the direction of
Well, no, here, what it's telling you is that the current is going in here, right? This is into the page. So it's going this way in here, and it's coming from behind, going over front, coming from behind, going over front, and it's going to come out here. That's what the dot means, right? So this is just this. If it's coming from in behind the wire, in behind the solenoid, like this, so the wire is curling in behind this piece here and coming over top like this.
you don't have to
No, this is just telling you if it's going into the page here and out here, it's starting here. Okay? This one here, it's starting here and it's coming out here, so it's going over the top and coming behind, right? So then that means that our north is going this way. This one here, we have X, so it's going in this way, and it's coming from behind over top on this number 4, so north is going this way. Okay? And so it's essentially telling you which way, which poles, this would be the north end of the magnet inside, this would be the south end of the magnet inside.
But like, I don't know why. Like the third one, why the hand is
This one? Because I'll get a new picture. Okay? So this one here, it's going in here. So it's going to start and it's going to go over top at the beginning. It's going over top and curling in behind. And it's coming out over here. Because it's showing that it's going over the solenoid first and then behind. Okay? It's just showing you which way it's flowing. Is it flowing this way over it, or is it flowing this way over it? Okay? And remember, this is only for, if we're using our left hand, it's only for electron flow, the negatively charged particles. Okay? If it's a flow of positive charges, you would have to flip to your right hand. Okay. So a solenoid or an electromagnet is what it can be called. has many applications because its magnetic properties can be turned off and on as the current is turned off and on. So what do you think would be some examples of using electromagnets? Where would we use them in real life? In a solenoid valve? Well, you know what? I'm going to write it down because I don't understand enough about vehicles to say yay or nay. It has the word in it. What about in, like, at metal yards? Scrap yards, that's the word. Okay? They have cranes that swing that big magnet over. They turn on the electricity. They pick up the scraps of metal. They go over to where they want it to be. They turn off the electricity, and everything is released from that magnet. Okay, so in scrap yards. Another one is you see them on TV all the time, but in safes, there's magnetic locks. Okay, a lot of the times it'll say this safe can't be opened until 7 a.m. It's on a timer for electricity. Another one where electromagnets or solenoids are used are in bells. You know, when you go and you can hear bells ringing, but you don't see a physical bell ringing. A lot of times it's just a magnet that shuts on and off in different parts of the, like they have a string of bells and it will turn off and on and they'll strike the bell, the clanger inside. I've seen it done. Okay, this one here. It says determine the direction of electron flow through the solenoid. Label the ends of the solenoid with the correct polarity. So it's already actually labeled, but the thought process is we see that the magnetic field goes like this. Oh, sorry. The magnetic field flows like this. These are the printed lines. So this is information given to us. So what do we know about magnetic fields? It flows from what to the what? Oh, you were so close. Flows from the north, out of the north, and into the south. Once we label north and south, we can then use our left-hand rule in regards to a solenoid because we see that this is a coiled wire, so we know we're dealing with a solenoid or an electromagnet. They're synonymous words. And so I'm going to stick my thumb out in the direction of north. That means that my fingers are showing me the flow of electrons, and the flow of electrons is coming from behind and working over top. Okay, so which way does it show coming from behind and then over top? This way here shows us going over top first and then behind. And this one here says from behind and then over top. So our flow is this way, from the bottom to the top, moving in this direction. So our electrons are going to come in this way, and they're going to go out that way. Okay? So on the original picture, the only thing that's labeled in this diagram are the arrows in the magnetic field. But it provides us enough information because we know that the magnetic field flows out of the north and into the south. Okay?